All right, welcome back to Physics 325, Optics. We're on video 2 of week 3 now, and what we're talking about here is a macroscopic picture of the interaction between light and matter. Last video we talked about a microscopic picture. In other words, we looked at atoms as small dipoles that can be oscillated by the electromagnetic field, and as they do so, they re-radiate their own fields in such a way that we have a light which slows down at the interface. As it travels through to a new material, the speed of light will change. And the ratio of the speed of light in that collection of atoms and the ratio of that speed of light in vacuum to the speed of light in the collection of atoms we call the index of refraction. And we came up with an expression for the index of refraction. We found that it's generally frequency dependent. So now we're going to do a more broad picture. We're just going to look at things macroscopically. We're going to forget about atoms. There's 10 to the 24 atoms in the small, centimeter by centimeter by centimeter, or thereabouts. So we're just going to neglect the discrete nature of the matter, and we're just going to say that it's made of some continuous substance with electronic properties, epsilon and mu. And given those electronic properties, we're going to derive things like the fact that light will reflect, light will refract as it goes through a medium, and how much of it will get bounced off and how much will go through, right? And that's our goal for today. I have to say this is a challenge. This is something I struggled with at the beginning of this course. Do we teach it? What we're going for today is a real solid physical intuition of why light bends as it goes through an interface, why it reflects. All right, we're looking for a physical picture of what's going on here. Another way to teach this course is just to say that it happens, and we'll move on and not worry too much about what happens at the interface. But I think it's very important to have a picture of the physics of what's going on with reflection and refraction before we move on to more advanced topics. The challenge with that is it's more mathematically demanding, of course, than just saying, well, it just happens and forget about it. So we're going to go through some equations today that is pushing the limits of the prerequisites of this course. I don't expect you to memorize the derivations. I hope that you can follow them and at least understand the picture of what's going on here. What we're going to end up with is something called the Fresnel equations, which tell us exactly how much light is bounced back and how much is transmitted given an index of refraction, or rather a ratio of indices of refraction between the incident, what the light is coming from, and the transmitted, what the light is going to, materials. Okay? So I have an old piece of glass here I just found, and as you might see, there's some reflections happening here. Right? I can kind of really narrow in on it and have a picture like this, right? Where I'm shining light through and some of it is bouncing off, some of it is transmitting, and I can change the angles and I can have it pretty much a normal interface, but there's some transmitted and some reflected field. So that's interesting. How are the angles related between there, and how much gets reflected versus how much gets transmitted? That's what we're interested in today. And to understand that, we have to note and admit to ourselves that the situation is somewhat more complicated. If I just look at the field here, as I'm shining the laser pointer in, it's a fairly wide beam. If I move into a millimeter by millimeter, or even less, say a micron by a micron, it's just this big bulk electromagnetic field, plane waves, which are coming in and interfacing and shaking the materials right at that interface. So the situation is more like this. We have incident plane waves, we have reflected plane waves, we have transmitted plane waves at some zoomed in region around here. And what's really going on right at the interface there is a swarm of all these fields that are all oscillating together in such a way that as they propagate, as we go a bit further away from the interface, we recover these well-defined beams of light. Okay, and that is what we're going to go for today. So the key here is that everything really is, all the magic is really happening at the boundary. So we're going to break it down this way, that right above we have two fields. We have an incident field, we're going to call E incident, and we have a reflected field, and we're thinking of these things as rays. These lines are just the wavefronts to remind ourselves that it's very much more complicated. It's kind of spread out everywhere across this boundary, and there's some transmitted field. Now, it's clear kind of what's going on well below here when we look at E transmitted and E reflected and E incident, but what we're going to do is we're going to look right at the boundary. So if we have the field directly above, it's consisting of these two fields, like directly above, a very small number above, EI and ER, and right below it's E transmitted. And what we're going to do is take the limit as that region, the height of that region, goes to 0. And we're going to find, by doing that, the fields are going to have to meet up. And in saying that they have to be stitched together in the right way, that the fields have to agree according to what electromagnetics tells us, electromagnetic theory, we're going to be able to get all the relations between this field, and this field. Okay? So, a brief reminder, because as I said, we're kind of pushing the limits of the prerequisites of this course. So a brief reminder of what we did last time, from last video. We had this displacement field. Okay, so when light was going through stuff, we had the original light going through the stuff and also all the dipoles that were creating their own fields. And we had to summarize both of those with this displacement field. And for media, such that the electric field isn't too strong, you're not kind of ripping the dipoles apart, we have a linear response. So this displacement field, the sum of the two fields from the polarization field of all the atoms and the original field, it just is linearly proportional to the electric field. We call that epsilon. When we write things in terms of the displacement field, we get the same Maxwell's equations back, and we have a wave equation that moves at a velocity v, except now it's not 1 over the square root of epsilon naught mu naught, it's 1 over the square root of epsilon mu, the material properties, and in generally that's going to give us a velocity which is slower than c. Okay, and the ratio of these two things gives us the index of refraction. Finally, just as a quick point, if the frequency cannot change, right? The frequency of light is just what it is. It's how many oscillations there are per second. So what's going to happen if we have this frequency wave relation, lambda f is equal to the velocity at an interface when the velocity all of a sudden slows down? We still have the number of, what is this saying? This is saying the distance per blip times the number of blips per second is the velocity. That makes sense, right? That's distance over time. But if the number of blips per second is constant and the velocity decreases, well, the wavelength has to decrease too. So you'll get kind of a smushing up of waves. They're happening just as fast, but the wavelength is shorter because the velocity is shorter. Okay, so that's this relation here. So effectively that tells us is that lambda gets reduced in a medium based in proportion to the index of refraction. And therefore we can write the k vector, which is proportional to 1 over lambda, is n times k naught. We're going to use that. So we plug in our plane wave in a material, we're going to get a factor of n in front of the k there. Okay, so that's an important point. So that's it for a recap. Now, warning. We're going to go outside the prerequisites. We're officially outside the prerequisites of this course now. Hello class, I am doing my Sunday late night editing of the week's videos, and this video is way too long. So what I was going to do is derive the electromagnetic boundary conditions using Maxwell's equations. I'm going to leave that as a supplementary optional video and just skip to the results here, because otherwise this video is just too mathematical and too hard. So if you'd like to watch it, it'll be linked in the description on the YouTube page. This is what we're starting with, all right? We have these boundary conditions relating the field above and below an interface. And we're going to use this. Because for us now, we're going to have the field above, which we call E1. So E1 is the field above, and that's equal to E incident plus the reflected, function of time, and E2, is equal to E transmitted as a function of time. All right, and we're just going to apply those boundary conditions to those. So notice when we do this, we can write out the form of these equations. We can do it for the perpendicular and the parallel parts of these equations. Okay? We do the perpendicular to the parallel parts of these equations. So look at the form of these equations, assuming plane waves, for the incident, reflected, and transmitted fields. This is what the boundary conditions both tell us, right? And notice the form of them. We always have a constant plus an exponential plus a constant plus this exponential is equal to a constant plus an exponential, or times an exponential rather. And here's the point here. The only variation of the functions happens in the exponential. So let's go to a particular spot. Let's say that our interface is at the z is equal to 0 plane. All right? So k dot r minus omega t, for either one of these k's, we don't know anything about the angle or the magnitude of them yet, or even the frequency, is equal to e to the I kx times x plus ky times y minus omega t. So for example, for the reflected field, krx, kry, reflected omega, right? So we can go anywhere we want along that plane. Those constants still have to hold. Let's just go to the origin. X is equal to y is equal to 0. All right? So we're going to have all the equations of the form a e to the minus I omega incident times time plus b e to the negative I omega reflected t is equal to c e to the minus I omega transmitted t. Okay? So at t equals 0, we see that a plus b is equal to c. A plus b is equal to c. What about time not equal to 0 as time goes on? Well, we still have to have a plus b is equal to c at all times, right? At all times, because these are constants. So the only way that these can be equal at all times is if the frequencies are all equal, right? So if not, the left-hand side, say, grew a little bit faster than the right-hand side, that these constants would be changing, right? So we would no longer have the possibility of a plus b is equal to c, right, if we plug those in. So the first implication of this, just by comparing the phase factors and seeing that they all must agree, is that the frequencies all must be equal. So omega incident is whatever it is, whatever is being sent in, and the omega reflected and omega transmitted have to match this. And this is a very common thing for linear systems. If you drive it at frequency omega, it responds at frequency omega, possibly with some delay or amplitude change. Okay? So these are equal at all times. In fact, that means for these equations here, we can just get rid of the frequency dependence, right? So we can divide both sides or multiply both sides by e to the I omega t, and we just have spatial dependence now. But we can do a very similar trick. So now, at x equals y equals 0, what do we have? We still have a plus b equals c. At x, y is equal to 0, 0, we still have a plus b equals c. But now we have these k dot r in the exponentials, k reflected dot r and k transmitted dot r in the exponential. And these all have to be equal, right? So they all match at the origin. Now I'm going to slowly move away from the origin, and these phase factors all have to follow each other, because these constants are fixed. They're whatever they were at the origin. So say I set y to be 0 and I only move along x, these all have to be wiggling at the same rate for these constants to always be equal for all points, right? So this tells us that the phases of these fields must match at all times too. K incident dot r is equal to k reflected dot r is equal to k transmitted dot r. What are we saying here? So this does not say that they're always equal at all places. This is saying at the interface, which we called z equals 0, but whatever the interface is, they have to match. The values of those dot products have to match at the interface. That means any difference they have is carried away in the z component, the z part of it. They all have to have the same values along that plane in order for these conditions to be met. Okay? So let's think about some consequences of this. All right? What are the consequences of this fact? The first consequence comes from the fact that, well, if we actually really write this out, let's just say that this is true, and we have this, what kx and x are. Let's look at an example. For example, what this is actually saying, ki dot ri ki dot r rather, is equal to kr dot r says that kx incident times x plus ky incident times y is equal to kx reflected times x plus ky reflected times y. It's a hard thing to say, but this is what this equation is telling us. Well, what is this? This is just an equation of a straight line, but maybe let's approach it a different way. We can do it that way. Let's just work along y is equal to 0, for example. It says that kx along y equals 0, kx times x is equal to ky r times r. So the kx components have to be equal, right? And these are constants. Similarly, if we just look along x, the ky components have to be 0. And this is also true for the incident versus transmitted field. So what does this actually tell us? The x components are the same, and the y components are the same. That means they're along the same plane, right? Remember, they can have different z's, but they all are along the same plane, and we call that the plane of incidence. So let's try to sketch. Let's try to sketch what that actually means. All right, so that says that, in 3 dimensions, I have something like this now, with our k's all in a line, and this is kind of like a side view, or a 3D view, I guess. If I have a full side view, I'm going to have something like this, and a top view. If I just look from the top, here in this case, by the way, this is z and, for example, x. And the top view, this is like x and y. They're all just going to be along a plane, right? All 3 of these rays are all happening along a plane, which we call the plane of incidence, right? So all that reflection happens along a single plane. And this is great. This greatly simplifies the work we have to do. So remember, we don't know anything about the z direction just yet. But we do have this side view picture. Okay, so let's tidy this up a bit. Let's look at this side view picture again and see what else we can glean from this. So we have our interface. We're going to have a K incident, and we're going to have a K transmitted, which is at some other angle. Let's call this angle here theta t, theta I, and some other crazy angle here. They look pretty similar, but assume that they're different. This is my reflected. What does this actually tell us? We don't know anything about z, right? The z's can be different, but what we have before is the xy components along the xy plane are the same. So I have that here's k incident times, if I do this, sine theta, k reflected times sine theta, and k transmitted sine theta. I have that k incident sine theta incident is equal to k reflected sine theta reflected, right? And we can use this fact from before that in a medium, so k is equal to n times k in a vacuum, and in this reflected case, they both are in the same n medium. This will tell us that k naught times n sine theta incident is equal to k naught times n sine theta reflected. Hopefully that's still on screen. The same k naught n's, so we have sine theta incident is equal to sine theta reflected. Or incident is equal to reflected angles, all right? This is the law of reflection. Theta I is equal to theta r. All right, how about the top and bottom ones? Well, now we have the other set of equations. We have n incident times k naught sine theta incident is equal to n2 k naught sine theta transmitted, or canceling out the k naughts, n1 sine theta incident is equal to N2 sine theta transmitted, which is Snell's law. All right? Or apparently his name was actually Snellius, so you might want to call it Snellius's law, but Snell's law will do just fine. So we have the law of refraction, which is Snell's law. Okay, let's take a breath. We've done quite a lot already, just by comparing the phases at those boundary conditions at the boundary, and how they have to be stitched together to be consistent with electromagnetic theory. We have that all the reflection and refraction happens along a plane defined by that incident beam, right? So that incident beam on the interface, it sweeps out the angle between the beam and the surface, sweeps out a plane, and all the magic happens along that plane. So we can really make it a two-dimensional picture. We don't have to worry about 3 dimensions anymore. We call that the plane of incidence. We also got that there's a relation between the angles because of these electromagnetic boundary conditions, and that is that the incident angle is equal to the reflected angle, and the incident and transmitted angles are related through Snell's law that we have written up here somewhere. Okay, so that's about as far as we might have gotten kind of in an earlier course, law of reflection, refraction, and Snell, plane of incidence. But we're going to go a bit further. If I have a milliwatt of light going into here, I want to see how many milliwatts are coming out, how many milliwatts are getting reflected. For that, we can also look at the boundary conditions and do a bit of math on them. So we have to ask ourselves, as these fields are coming in, is there a special preferred direction, right? If I have light, I'll make a nice beam of light here. If I have light coming in and reflecting off, it's along some plane, right? It's coming in, it reflects along that same plane. That's what we know. I guess it would be like that. That's all we know. What can we say about the direction of the electric field? Well, it can be anywhere in that plane perpendicular to that input k vector, right? So we need to think about, is there anything special about any of these directions, right, as it propagates? In free space, it's completely the same. It doesn't matter which peck. But there is a symmetry here, right? There's a plane of incidence. And maybe the fields look a bit different as they're oscillating along that plane of incidence versus perpendicular to it. In fact, you can see that they are. In the one case, as it comes in, as it's perpendicular to that plane of incidence, none of the field is kind of perpendicular, right? We don't have any E perp component as it's going in. Whereas in the other case, we have a combination of perpendicular to the plane and going into the plane, parallel to the plane. So there is a preferred direction, and we have fancy names for these, right? The S and the P polarization. So if the light is wiggling along the plane of incidence, we call that P polarized light. If it's perfectly perpendicular to that plane, we call it S for perpendicular. No, it's a German word, senkrecht, I think I should check, which is German for perpendicular. So we have P for along the plane of incidence, S for perpendicular to that plane, and those are the S and P polarizations. So for P polarized light, it's oscillating along that plane, and part of it is going into the medium, part of it is going perpendicular. For the other polarization, that is just completely going out of the plane and into the plane, and we can treat these two things differently. All right, so here's kind of a more three-dimensional picture of breaking them up. What if we had light that was not in one of those directions? Well, we just break it up into the S and P components and treat those separately, okay? And this, breaking it down this way allows us to analyze the picture for the S and P polarizations and look at the so-called transmission coefficients, how much light is coming out. Let's do P polarization. We'll do P polarization and we'll let S polarization, which isn't as complicated, I don't think, it's only one direction. We'll let you kind of walk through this on your assignment. So for P polarized light, let's actually draw the picture of what that is. Here's our K vector of our incident light, and that means our electric field is perpendicular to that. Right, and here's E input. Okay, so we can break up, our goal is to use the boundary conditions. We can break it up to the part that's along the interface and that's going into the interface. Right, so that's two beams here. We have E parallel part. So we have E parallel of the incident is equal to E incident. Well, what would it be? If this is theta, I have to think about this. This is theta, this is 90 degrees. This is 90 minus theta, I'll call that phi. And this is 90 degrees. This is also that phi. So this is theta here. Yeah, that seems to make sense. So I have the same theta here and here. So this is equal to EI times, looks like the cosine of theta incident. Okay? And it also has a perpendicular component. And this is with respect to this plane, this interface, right? So E incident perpendicular is equal to EI times sine theta I. All right? And we can do the same thing. We can do the same thing for the transmitted beam. Right? The transmitted beam has some theta here. And it's going to have some E transmitted part, which we can break up into a part which is perpendicular to the surface and a part which is, a part which is parallel to the surface and a part which is perpendicular in the exact same way. And we're going to get the same equations. All right? So we have ET parallel is equal to ET times cosine of theta transmitted. And similarly for the perpendicular part, ET sine theta. Finally, we have the reflected, which is very much similar, except we have to choose a convention for which way we're going to call the electric field. And let's see, if they should meet up when that angle goes to 0. So that's going to be going this way. And now if we see, oops, I'm going to keep the same color scheme here. If we see, we have the same kind of direction for the perpendicular part, or for the parallel part. I keep saying the wrong thing, but the perpendicular is now going down. Okay, so E reflected perpendicular is equal to minus theta. So it's going to be E reflected, negative E reflected sine theta r. And it's going to be the same form for the parallel. A bit bunched up here, but forgive me. Cos theta r. Okay? And this is what we have, right? We have these relations between these fields here. We also have our electromagnetic boundary conditions. So we have that E1 is equal to E incident plus E reflected. And E2 is equal to E transmitted. And we also have that E1 perp is equal to N2 over N1 squared, E2 perp, and that E1 perpendicular or parallel is equal to E2 parallel. Okay, so we can throw all this together. We've set up, the hardest part about this problem is really setting up the coordinate system like this. But we've set up the coordinate system, and we can just see what the equations tell us. All right, so let's do that. I'm going to chop off a bit of this to clear some space here. Let's just start plugging in those boundary conditions. So E1 parallel is equal to E2 parallel. Okay, so let's see what this actually tells us. Let's see what this boundary condition tells us. Well, we got E1 parallel is the cosine, so that's going to give us E incident cos theta I plus E reflected, I almost wrote a negative sign there by accident, theta r is equal to E t times cos transmitted. Okay, and what we care about is not so much the absolute value of these things, but we care about the ratio between them. So what we're going to do is we're going to divide everything by the input, and we're going to define R is just the ratio of the reflected field to whatever came in, and T is similarly the ratio of the transmitted electric field to whatever came in. And we're also going to note from the law of reflection, LOR, that theta I is equal to theta R, and rewrite this equation as such E1 divided by E1 is equal to 1. So that's going to give us 1. We'll factor out the cosine plus r times cosine of theta incident is equal to t, et divided by ei, divided by cosine of theta t. Okay? Boom. There's our first equation that we're going to have, which relates to reflected and transmitted. We have one equation and two unknowns right now because we're trying to determine t and r. Let's find out what the other equation tells us. Well, that tells us that E incident times sine theta incident minus now ER times sine theta r, which we know is sine theta incident, is equal to, what do we say it is? It's N2 over N1 all squared times sine theta transmitted. Okay? And let's write this N2 over N1 times N2 sine theta t over N1. And note that from Snell's law, it says that N2 sine theta t is equal to N1 sine theta incident. So this is equal to N1 sine theta incident, N2 over N1. N1 sine theta incident divided by N1 is just sine theta incident. Okay? So this whole thing is now equal to N2 over N1 sine theta incident. And we can cross out the sign on all parts of this. Dividing by EI, we have our second part of this equation, which is 1 minus r is equal to N2 over N1 times t. Okay, great. Let's put a box around that. And now we can just solve. Now we can solve for our reflected and incident components. I'm going to clear up a bit of real estate here. Okay, so this is saying that t is N1 over N2 times 1 minus r. N1 over N2 times 1 minus r. And we can plug that into this equation here. So this tells us that 1 minus r, 1 plus r rather, times cos theta incident is equal to N1 over N2 1 minus r times cos theta transmitted. Okay, and we can just solve for r here. So let's do that. Let's just blow it up and brute force it. We'll get an N2 on the other side just to make our lives a bit easier, I think. And we get N2 cos theta I plus r N2 cos theta I is equal to N1 cos theta t minus r N1 cos theta t. All right, just blasting away, expanding the whole thing. Let's isolate the r's to one side. So we get r times N2 cosine theta incident plus N1 cosine theta transmitted is equal to whatever's on the other side, which is going to be N1 cos theta transmitted minus N2 cos theta incident. Okay, so that tells us that R, our reflection coefficient for P polarized light, is equal to N1 cos theta t minus N2 cos theta I divided by N2 cos theta I plus N1 cos theta I. N1 cos theta t, rather. Whew. That is our first Fresnel equation. That's a lot of work. It's a lot of work. So we can now just plug in the other equation that says that t is equal to N1 over N2 times 1 minus r. So t is equal to N1 over N2 times 1 minus r. I'm just going to call cos theta t ct, if you'll allow me. So that's going to be 1 minus, this is going to be N2 cos incident plus N1 cos transmitted minus N1 cos transmitted plus N2 cos incident divided by N2 cos incident plus N2 cos transmitted. Pardon my laziness, but it's just would be a lot of cosines to write. So we get some cancellation. These two cancel. The N2s are going to cancel and bring out an N1, and that gives us that T is equal to 2 N1 cosine theta incidence over the same denominator as the reflected. Cos theta incident plus N1 cos theta transmitted. Oh boy. Okay, that is a lot of algebra that we just did, and this is what I was worrying about at the beginning of the lecture here, but I think we got it. We got there, and these are the Fresnel equations. We can do the exact same thing for S polarization, and we get very, very similar results. Okay, and I'll let you guys work that out a bit later. We can plot these, and this is what we get for the two polarizations, the two reflection coefficients in this case. It starts out very small, and as we go to larger and larger angles, that means if you go to a more and more of a glancing angle, we get closer and closer to perfect reflection. So try this. Next time you're walking down a hallway, say in the lab wing or when you're in a building, what you can do is just look along the distance, look at lights, say along a kind of a glossy hallway, and the reflection, they become mirror-like as you look further and further away. And what's going on there is you have that very shallow angle, which in this case means a very large angle, and you're getting a very large reflection coefficient. Something to keep in mind is that this is for the fields, not the intensities that we actually measure. For the intensity coefficients, we can just use the fact that we have our expression for intensity is proportional to the field squared. Okay? In a medium, we have a factor of n out front, which we briefly mentioned last time, but it doesn't really matter if we're in the same medium for the reflected field because they're in the same ends, and we look at the ratio of the reflected fields squared is going to give us the amount of reflected intensity, the amount of power per unit area, which is coming out. All right. For the transmitted, it's only a slightly bit more subtle because we're now going into a medium. The angle changes, so we get a bit less flux going directly into that medium, and we're in a new medium which carries a different amount of power because there's a different index of refraction. So the picture here is we have light which is coming in, it hits an angle, and there's a more narrow flux because it's now bent at an angle here by a factor of cosine theta. So all we have to do is multiply by these cosines, and that kind of corrects for this change in flux right below the surface versus right above, and we get the transmission coefficient. All right, and this is what they look like. Let's zoom in on those very briefly because we're almost at the end here. We've done quite a lot. This is what they look like. We have the intensity and the reflected transmission coefficients. They add up to 1 as they should. And going from air to glass, say like we have here, we have some interesting features. Right? We have the fact that the reflection at normal incidence is, looks like here, about 4%. We can derive that directly from the wave equation. That means when I do this, about 4% of the light is bouncing back at the camera here, bouncing back out of your screen, and 96% is going through. There's also something interesting. We have slightly different behavior from the S and P polarizations, and that's something we're going to dig into in video 3. But there is kind of an interesting feature is that reflection vanishes at some point. We get a vanishing reflection, and that is something that happens at what's called the Brewster angle. We have, for light which is wiggling along the plane of interface, for one precise angle, we get 0% of it reflected, 100% transmitted. Very, very neat. We'll go into that next video. There's also something interesting. We go not from air to glass, but glass to air. There's an angle for which no light escapes. This is the phenomenon of total internal reflection, which we'll talk about next time as well. So there's a lot of neat physics after all this hard work. We can predict not only the powers, but we see some new phenomena emerging. But we've done so much today. Everybody needs a break. Go get a cup of coffee and pat yourself on the back for getting through it. And we'll go through that stuff next time. We'll just take the last minute to summarize. So basically, by looking at the bulk material, the epsilon and the mu of matter, we could apply the boundary conditions to relate what the fields were immediately above and below an interface in this kind of complicated situation. We had light coming in, part of it goes through, part of it reflects off. By looking at the phase relation between those fields, we could already glean a few facts. We could look at the fact that everything was going to happen along a plane, the plane of incidence. The law of reflection holds such that the reflected angle with respect to the normal is the same, just on the other side. That's a law of reflection. And the angle of the beam as it goes through to a new medium is related to the incident angle via Snell's law. All right. Finally, we looked at the amplitudes of these fields by looking at the electromagnetic boundary conditions and what they imply, and we derived Fresnel's laws, which relate the intensities and predicted some new interesting phenomena, which we'll talk about next time. So great work getting through this one, and we'll see you next time.